Hi, everyone. Thank you and welcome to the 36th session of the International IVF Initiative. This session is entitled In Silico Fertilization. Please visit our website, ivfmeeting.com, to view recordings of previous sessions. You will also find information about upcoming sessions on the same page. Thank you for logging in and listening today. We are so pleased that you have joined us. We encourage you to please use the Q&A function to ask questions during the session. We have a special treat for those of you tuning in today. At the end of our session today, you will have the chance to win a free subscription to RBMO after we quiz you with 3 questions. RBMO stands for Reproductive Biomedicine Online, so make sure you stick around. I am honored and excited to be co-hosting this session of the International IVF Initiative with Dr. Jacques Cohen. Now, Jacques is a man who needs little introduction. I'm sure all of you have heard his name in the industry, but for the few of you who haven't, his bio is available when you click his name on our session 36 on the website. Dr. Cohen has been instrumental in the field of IVF for his contributions towards the development of several procedures, over 300 publications, several textbooks, and a few patents. He has founded or co-founded different companies and professional organizations, including, of course, my favorite organization, i3. I would also like to congratulate him on his recent Lifetime Achievement Award given to him by the SRBT. Congratulations, Jacques. I could probably spend the full 90 minutes of today's session overviewing his accomplishments, but the only thing bigger than Jacques' CV is his humility, so I won't do that to him.
Thank you very much, Shaista, and welcome everyone. A really nice introduction, and thank you for the congratulations. I'm a little worried about the lifetime thing and the lifetime award, but I'll get over it, I hope. I'm very happy to share this session with you. If you wonder who Shaista is, you may ask if you've never seen her before. She's always behind the scenes. She has moderated several sessions so far, and I'm very happy to share this one with her. She has been an I3 core member from the start. I think this happened in late March when the lockdown just started in the Northeast. She's amazing, talented, soft-spoken, intelligent. She is very important. She's a chocolate lover and a gamete lover. So very accomplished. Shaista is a clinical embryologist with over 7 years of experience. She's currently working at Reproductive Biology Associates. I worked there about 100 years ago. And so I'm still very much attached to the group. Shaista graduated magna cum laude with a bachelor's in biology from the University of Georgia. She has received a master's degree in reproductive clinical sciences from EVMS, where she was bestowed the Georgiana Jones MD Award for academic achievement in reproductive clinical sciences. Her passions include reading, hiking, and of course, chocolate. So we have an amazing program planned for the next 90 minutes or so that will capture aspects of the future of IVF. So Shaista, I'm a little bit confused. I mean, Jacques has put this all together, this program. It's a Palmer production, is what we call it now, Palmer production. And I'm a bit confused about the title of this session. And since you actually read things, and I rarely do, I rarely read. You know, I used to be an editor, and editors don't read very much. So what does in silico stand for?
So in silico refers to in silicon, which stands for scientific experiments or research, conducted or produced by means of computer modeling or computer stimulation. Silico refers to one of the components of computer chips. At least that's what Wikipedia has to say.
Wikipedia, okay, so then it must be true. All right, great. So we have an amazing program on in silico today with 4 speakers who will cover theoretical and practical aspects of in silico applications such as facial matching and recognition, 3D imaging during surgery, immortal sperm revived as micro-robots. So imagine all that is going to happen in the next 75 minutes or so. Our speakers are Dr. Eyal Gruss from Israel, Joshua Rackstraw from Spain, Professor Nicolas Bourdel from France, and Dr. Veronika Magdanz, also from Spain. We are also, as usual, here with the team of I3 who are working behind the scenes to post your questions to our speakers. We encourage you to ask your questions using the Q&A section and not the chat function. So Q&A, please. We will try to address as many questions as we can during today's session. These are exciting topics, so please, please let's hear what you want to ask. Okay, back to you, Shaista, and introducing the first speaker of today.
Absolutely. So to start, it is my great pleasure to introduce our first speaker, Dr. Eyal Gruss from Israel. Eyal is a machine learning researcher, consultant, and teacher, working mainly in image and language processing. Eyal has a diverse artistic and industry background, including medical, financial, cyber, sensors, ads, web, real estate, and creative. Please check him out at eyalgruss.com. Eyal holds a PhD in theoretical physics and is also a new media artist creating and using generative algorithms. Dr. Gruss will speak today about Computer Shows Why, Visualizing Machine Learning and Decision. So without further ado, I will hand the mic over to Dr. Gruss.
Hi, everybody, and thank you for having me here. Hopefully you can see my presentation.
Yeah, looks good. Thank you.
Okay. So this talk would be about visualization methods for machine learning algorithms in order to explain, to interpret, to have transparency and visibility into the decisions of machine learning models. So I'm Eyal Gruss. I was already introduced. Thank you for the nice introduction. I'm working with AIVF, doing machine learning for embryo selection, and also with gene tools, doing diagnostic histopathology for sexually transmitted diseases. I will show today examples from both startups where we apply these kind of visualization methods and how we benefited from them. Why should we visualize or explain or interpret our models? So first we have debugging for the research and development stage. Then when you want to sell the product and when you deploy it and want the end users to use it, you need to build trust in your model and its predictions. And finally, in the production stage, a model that can explain itself can be very useful, supporting decisions, even if it gives an alternative view that the expert contests, it could be helpful. And in general, it can give insights to help the expert make her final decisions. And as far as I'm concerned, the last two are also part of my responsibility as a data scientist. And maybe it's more important to have a model that people will actually use. And this could be more important than a model that is maybe a little bit more accurate, but nobody uses it. And these aspects are becoming increasingly important as we have ML models in critical systems, for example, autonomous vehicles, of course, also in the medical domain. And then we have regulations that require fairness and transparency as we have in the GDPR or anti-discriminatory laws. So this is an example from a model from an autonomous vehicle. And you can see in the visualization, it is focusing on the edges of the road, on the markings on the road, and on the cars in the side of the road. And it's a good thing for a model that is driving a car to focus on these parts. This example, a little bit more funny, shows what a model thinks represents a barbell. And you can see that it is always attached to a human arm holding it. And this, of course, can have some impact on the model's performance. In this example from the line paper, you can see the husky dog was classified as a wolf. And in the explanation, we see that this happened because the model focused on the background and actually completely ignored the animal itself. The background, the context may be relevant. We may want to consider it or not, but here we can see actually it's dominating and the animal itself is ignored. And in this example, by trucks, they try to recognize products in supermarkets, and they want the model to focus on the label. But they've seen here when they use this method to debug the model that actually it also captures the reflection, which will not be relevant for classifying the products. And maybe a more relevant example from the medical domain, you have here a detector trying to discern between benign and malignant lesions, skin lesions. And it turns out that doctors mark the lesion with some purple marker. And you can see, while for the case with no markers, the model focuses on the lesion itself. For the marked case, actually, you can see in the heat map, I'm not sure if you see my cursor or not, the model ignores the lesion in the middle and actually focuses on the markings. And we may want to hide the marking for the model in this case. So actually we have two issues here. The first one being that the marker is mistaken for the lesion, and this is obviously wrong. The second one is that the marker may leak some clues about the doctor's opinion, and we no longer have the model giving an independent evaluation. So this is some kind of cheating. So we want the model to be right, but we also want it to be right for the right reasons. You may have heard about the paperclip maximizer fallacy. And the idea is that the model will always try to cheat, especially when the metrics are too simplistic. And visualization methods can help as checks and balances against this behavior. So I will consider a few methods for visualization. The first two are attribution visualization, showing heat maps or saliency attention maps. And they can help both make sure that the model is focusing on the right parts. This is helpful for debugging. And also it can explain why the model made its decision, and this can help decision support. So the first method, guided backpropagation. This is a method giving a high resolution heat map, but it highlights a low level feature, so it's less semantic. And here we're looking at the input image and asking which pixels affect most strongly the output of the model. So in this case, the model is looking at the image of a border collie, and it predicts a border collie. And when we ask for the heat map for this prediction, we see that it highlights the eyes and the nose as the parts that affected most strongly the output, the prediction of the model. And for a real use case, with gene tools, we have a detector detecting different kinds of pathogens. For example, this is atopic vaginitis. And for different cases, the doctor is looking for a specific kind of cells, and the model gives a prediction. And in the heat map on the right, you can see that it's actually highlighting exactly the same cells that the doctor is looking for. So this helps us be more assured that the model is doing the right thing. And most recently, we had a problem with false positives. And this kind of visualization helped us find out that the model is focusing sometimes on dust particles on the lens and mistaking it for the pathogen. So this is not only for sexy PR slides, it actually helps us debug the model. Going to AIVF, I know you've already seen this, but I need to explain. So this is a heat map visualization for a model predicting implantation probability. And you know, this kind of model sometimes is criticized for maybe amounting just to simple edge detection. But you can see that the edges marked are actually important and semantic, like the cell divisions or the pronuclei. And these are very relevant edges for predicting or capturing the events that are important for predicting the quality of the embryo or the implantation potential of the embryo. So it helps us make sure that the model is actually looking at the right things, giving its prediction. A second method called GradCam. This is a low resolution method, but now it highlights high level features that are more semantic. Here we are looking at the last spatial layer of the network, and we ask which parts of this layer determine the predicted class. So here we have an image, put it in a recognizer, and it says there is a person, some sheep, and a border collie. Now we can ask, why did you predict border collie? And it shows us this heat map around the border collie. We can ask, why did it predict sheep? And it shows us the sheep. Now we didn't learn any new insights here, but it helps us make sure that the model is predicting stuff because it's actually looking at it. But it can also be helpful for explaining. So in this case, this is the border collie. It predicts border collie. It's the only thing in the image. But now I actually can learn something new. I learned that border collies may be characterized by these large ears. And if I'm a dog expert, this can help me be reassured that indeed the prediction of the model, the border collie, is the correct prediction. So in this paper, they use this method to consider bias in the data. They had a data set where most of the doctors were men, most of the nurses were women. In the first row, we can see an example where the model predicted correctly this woman is a nurse, but why did it do it? It's focusing on her womanly hair. And this is maybe right, but not for the right reasons. So they try to make the data gender equal. And on the balanced data set, now it's predicting nurse because she has the uniform of a nurse. And in the second and third row, the model before predicted that the woman is a nurse because it was looking at her short or at her womanly hair. And now for the balanced data set, the model is predicting she is actually a doctor because it's looking at the stethoscope. So this helped us make sure that the model is right, but also that it is right for the right reasons. The last method I would consider, embedding visualization. So here we take the actually last layer before the classifier in the neural network. And this is, you can think about it as learning a high dimensional embedding or a condensed semantic representation that the model learned from the data. And this can be useful for various downstream tasks. Now, this embedding, this representation is very high dimensional, say 4,000 dimensions, and to visualize it, we need a way to reduce it to 2 or 3 dimensions. This is called dimensionality reduction or manifold learning. And in the simplified example, I have this S, which is a 2D surface embedded in 3D space, and I want to project it to 2D space while preserving the local structure. What do I mean by local structure? I mean that if I'm an ant living on the S, I cannot jump from the red to the yellow. I have to go over on the surface through the orange. And I want my projection method to spread out the S in a way, as you can see on the bottom right corner, to capture this kind of, respect this kind of local structure. So two popular methods to do this are TSNE and UMAP. Just showing these slides so you can see these nice 2D visualization. On the left, you can see separation between different classes. And we use the TSNE method at GeneTools to show the embedding, the learned representation. Of course, here you don't see anything, but we do have the labels, so let's color them. And now each color presents a different pathogen or prediction. And first, you can see there is a good separation between the different pathogens. Second, you can see the circle in the middle showing some maybe mislabeling, some errors that can help us find them in the data, in the annotations. But most interestingly, the red and the blue, they are actually the same pathogen, but using a different diluent. And also the pink and the purple are, again, the same pathogen, but each one with a different diluent. And we designed a system to learn a shared representation for each pathogen, even if it uses different diluents. And this kind of visualization helps us show and be assured that the model actually learned this shared representation, because the pink and the purple are mixed and similar to each other. And so for the red and the blue, they are mixed between them and similar to each other. So this is a very non-trivial result, helping us being assured that the model works as expected. To conclude, I would like to suggest the dashboard metaphor. So going to the world of autonomous vehicles, on the left, we have the Tesla Autopilot, which is autonomous level 2 or 3, sometimes called hands-off or eyes-off. There is a person near the steering wheel. He has all these controls and dashboard, and he can take control if needed, but using AI to drive the car. And on the right, we have a Google Waymo. The people are in the back seat. You don't see anything almost on the dashboard, and they cannot intervene. So the car needs to be responsible for itself. I believe that at the current times, medical AI solutions should be designed with the approach considering the man in the loop, or the expert at the helm, if you wish, as depicted more to the left side of these two examples. And I hope I may have convinced you that the visualization we have seen today can be an important and useful means to achieve this. So the takeaway for the talk is we soon have AI embryologist robot that will replace you all. But you know, maybe this is not a good idea. Let's not do this. Maybe AI black box saying good baby, bad baby. Let's not do this. So what I suggest instead is to think about it as an AI peer consultation or a decision support machine, and take this very dirty data sometimes and use various machine learning models to have a rich dashboard of scores and visualizations, and they may assist the human expert in explaining and supporting their decisions and giving them insights to make better decisions. So you can find the slides in these links. I actually have a whole workshop on hands-on playing with these methods online that you can check out in this playground. And thank you very much.
Well, thank you, Eyal. That was a great presentation. A little complicated at times for embryologists, but I think we're getting more and more acquainted with the terminologies. We're getting more and more acquainted with the features and the thinking behind it, and you particularly emphasized the latter. Now, there's already a lot of questions that came in. I'd like to ask you one or two questions, if you don't mind, and then we'll go on with the next speaker. So one of the questions is, how do you not introduce bias into algorithms? And my question about that is that really such a problem if you introduce bias? Because humans are not so bad in cognitive behavior, not so bad in judging circumstances and form and features that are visible. Are we just simply not good enough? Why would we be worried about bias?
Because our algorithms, machine learning algorithms are trained on data. And if we train them on data from West Europe and North America, we can expect that they will give not so good results or even bad results in Africa or in Asia. And this is a problem. If an algorithm does not work for someone with different skin color or other conditions, we have a problem here. And we need first and foremost to be aware about this. And of course, make, design, and train the algorithm in a way that they will work for all the population.
But what if it just works for a certain country or a couple of countries? Like it works for South America, but it doesn't work for Eastern Asia. Is that such a problem? You would have two algorithms doing more or less the same thing, but just in different regions. Would that be something you'd be satisfied with, or that's not the aim? That's never good. I just wonder.
So you have to be aware of this. If you have a tourist coming from Asia, will you use the other model? Can I trust you to do that?
Yeah.
So, and you know, there are various different indirect differences between countries depending on the public medical policy, if it's financed or not, and the family culture, if they want more or less babies, and this affects the age of the patient and their socioeconomic status and history. And we must be aware of these differences when we build a model and try to also deduce cross models, cross countries, cross clinics.
Mm.
And also the data itself is very biased. You know, I have information about the success of embryos that were implanted. If they were discarded, it's like sensor data. I do not have this information. So there are a lot of biases and imbalances in the data that we need to take into account.
Yeah, I'm pretty impressed. I'm very impressed with your ability to jump from one field to the next. That must come in handy, right? You go from physics, you go to you go to different areas of medicine. You jump around. Art is not something you shy away from. So you know, games, you don't shy away from games. So this must be helpful, I guess, right? If you have this wide vision and the abilities of these different technologies to come all together and converge in a new application. Let's say something like assisted reproduction. Right, I think that's probably an advantage rather than having the narrow narrow view that most of us, I think, or talking about myself, the narrow view that we tend to have when we approach a new problem in our own field. So,
well, I guess like basic scientific training is always useful. Problem is that physics is very hard, so physicists go to more applicative domains like finance and medicine and machine learning nowadays. And the nice thing about machine learning is that it is really applicable for many domains and useful, solving real world problems. And actually, I find it very nice that I can use like simple metaphors to think about ideas and then implement them, and they actually work and they help me solve the task at hand.
yeah.
So this is a really nice set of tools to attack different problems.
Yeah, I can see there are not enough hours in the day for you, and there's so many things you'd like to do. Well, thank you again, and don't go away because later we have a Q&A, and I will get back. I know it's late, but have some coffee and we'll get back to you, okay? So thanks again, Eyal.
Thank you.
It's my pleasure now to introduce Joshua Rackstraw.
Hello.
Who is from Spain and is the product owner of Phenomatch, a platform that uses AI to rank potential donors by their facial resemblance to the recipient or the recipient's partner. Josh is also an AI ambassador with an interest in ethics. He just published a book. He probably is going to talk about it. He just published a book on ethics and AI, and he's one of the authors of the Zaragoza Declaration, a treaty on AI principle written earlier this year. And he's going to speak today about AI facial matching for gamete donors and recipients. Fire away, Josh. We're looking forward to this.
Thank you very much. I would be very embarrassed if I didn't make one small correction there, I'm afraid. I just want to say I was part of a workshop which created the Zaragoza Declaration, and I did also translate it later. I wouldn't say I was one of the authors.
Okay.
So sorry about that.
Right. No worries, no worries.
Okay, so I'm going to share my screen. Hopefully you should be able to see that now. Okay then, so firstly, thank you for that fantastic introduction, Jacques, and thank you to Shaista and Giles and the rest of the i3 team for letting me be here today. It's obviously a fantastic honor to be alongside Jacques and the other experts. So yeah, like we've said, I'm from Phenomatch. I'm the product owner. And what we do is facial matching for donors and recipients. So we find the donor with the greatest resemblance, and that's the phenotypic resemblance on the face, to the patient or the patient's partner. As Jacques said, we do focus on the traits which are phenotypic. Those are the ones which are passed on to the children via DNA. And the objective, of course, is to increase the degree of facial resemblance between parents and donor-assisted children. So this is not going to be a sales pitch, but I do want to start with some numbers just to demonstrate the stage we are at. Because I know a lot of the talks today and a lot of the time that we talk about AI, we're talking about the future, or we're talking about research that is being done. But just to be clear, we started operating commercially in 2018 after many years of research and investigation and design. The first Phenomatch babies were born in May 2019. That's right. And we work with around 100 clinics. And I'm very proud to say we've helped around 7,000 families get started. And that's something I always try to remind the team that I'm working with, that although it seems like we're just working on computers all day, every day, what we really do is something which is, you know, helped in that sense. So how did we build the algorithm? Well, the initial data set was 864 human faces from 108 families. There were various ethnicities, of course, which is incredibly important. And there was a 1-to-1 gender ratio. What Jacques was saying earlier about bias in terms of embryos is incredibly and much more relevant when we're talking about the human face. Ethnicity is essentially a phenotypic trait. So that's something we spent a lot of time investigating, doing research, making sure we could avoid that bias. The one-to-one gender ratio, of course, was also important. And because gender is not phenotypic, it's not inherited, our algorithm works whether you're a man or a woman, and whether you're looking for sperm or whether you're looking for an egg donation. So of course we work with gay couples, lesbian couples, and of course heterosexual couples. So in terms of testing, the last tests which I personally did was about 2 weeks ago, and we gave the algorithm 600 human faces. And within those 600 faces, one of the people was me, and the other, another one was my brother. And the algorithm, it takes a couple of seconds essentially to identify very accurately two siblings. And of course, the reason it does that is because we share genetic material, so we have a very similar phenotype. So many people think of PhenoMatch as facial recognition or some variation on facial recognition, and that's understandable. People know what facial recognition is. But what we do is quite different. And I'm going to show you a photograph now. And there will be two people in the photograph. And I know that a lot of, we have some people from AI backgrounds, we have some embryologists, we have some doctors, but I think even if you're not a medical professional, you're going to see some facial resemblance when I show you the next two photographs. And I'm going to give you a second just to make sure you spot it, but you might be able to see some similarities. Okay, I think that should be enough time. This is my mum and my brother, and this photo was taken at my brother's wedding last year. This was pre-COVID, of course. This was before masks. And you can see a couple of traits like the shape of the nose here, and also the teeth and the smile, and also the hairline. You can see a certain similarity. I don't know if you're also seeing that in me. I don't think we look that similar, realistically. So one thing that's fantastic about our algorithm is that it doesn't just focus on individual traits. So right now the industry standard is, skin tone, eye color, hair color, this sort of level of specification. What we're able to do is capture the look of the person and use that to compare and find the donor with the greatest resemblance. Let me just have a little think. Okay, so I could talk about PhenoMatch forever. It's something I'm very passionate about, and something that I feel very lucky to be involved in. And I hope that we're going to get some fantastic questions, both after this talk and at the end. Please feel free to ask me absolutely anything. Like Jacques said, I'm also going to talk a little bit now about ethics, because I really love AI ethics. I really love Black Mirror. I really love The Matrix. And I also love ethics in real life. It's not as interesting, but it's still interesting to me. So yes, I was part of the workshop which developed the Zaragoza Declaration. This was lucky enough, this was a European Union funded initiative on artificial intelligence, and we were lucky enough to have it in our city, which is Zaragoza, which is right in the middle of Spain. And so we did a series of workshops, and then later I was the official translator, which is something I'm incredibly proud of. I've included a link here at the bottom. You can also find it just by searching Zaragoza Declaration, AI ethics. If you don't have time to read or you're not too interested, the main idea, well, what I think the main idea is that AI is too powerful in terms of a tool. It's too powerful for the benefits only to go to a small group of people in Silicon Valley. AI is something that should really be used to benefit all of us, essentially. And I'm not going to talk too much about the bigger problems related to artificial intelligence, like Facebook or racial bias, or even democracy or screen addiction. I'm going to focus on PhenoMatch and a couple of the things that I'm very proud of. So let me see. So the first point then, technology for good. We've been lucky enough, and some would say blessed, to have found an application for artificial intelligence which really does help to solve a human problem. And you might say, well, anyone can look at photographs and decide which two people look the most similar. And that's true, of course. But in a situation where a bank or a clinic has 100 donors or 250 donors, you know, or it's a chain of clinics or a chain of banks and they have 3,000 donors, it would take a human being a long time to look through all of these photographs. So what we can do is put them in order. And then you know that the first donor on the list is the one that has the greatest similarity in terms of the phenotype. And so that's something which I'm really proud of in terms of it being something genuinely useful, I hope. We also have some tools to help avoid human error. So for example, we can do ethnicity verification based on the photograph. And that might seem a bit strange because, you know, if there's a doctor looking at the photograph or if the donor's characteristics have been input by a human being, why would there be a problem? And of course, they are very, very incredibly rare that these problems happen. But yeah, of course, when we're dealing with donor banks that have thousands and thousands of donors, then things can get a little bit complicated. So it's good to have technology that can help to check that kind of thing. Which brings me to my next point. What role should AI have? So in the situation that there is an ethnicity mismatch, so for example, we have a donor that is listed as Caucasian and they're actually, for example, Asian, then all the system does is notify the user, and the user is therefore able to verify that the ethnicity is correct or change the listed ethnicity if it's not. And another one of the questions we get very often from America. So in the United States, patients can see the donor photographs in many states. That's the situation. So the question that we get very often is, what happens if you get your donor, you find the one with the greatest phenotypic similarity, and you don't like them for whatever reason? You see the photograph and you're not happy with that donor. Well, if you disagree with the result from a perfectly scientifically valid artificial intelligence algorithm, you should completely ignore it. You should pick the donor that you like, or the donor, of course, that you think the patient would like in the case that you're a doctor. AI is just a tool in the toolbox, but we need a human being to decide which tool is best and most appropriate for the job. This is very similar, of course, to what Professor Gruss was mentioning before, in the sense that AI should not be a black box. It should be something we're able to control and understand. I see we're getting some questions through. We'll be dealing with questions at the end. I'm sure that Jacques will share those with me. Okay, so let me carry on then. The last thing I want to talk about is our role as AI ambassadors. So Jacques mentioned that I was an AI ambassador. It's not something that I call myself very often. I think that we're all AI ambassadors here, all of us, at least those that are dealing with AI, because we're here and we are sharing our work and we're explaining how the things work. And that's what an ambassador is. So why is it important then that we organize these events and that we sponsor them and that we help with them as much as we can? Well, it's in order to share the knowledge of what AI is and how it works. And when we do the Q&A, I hope we get lots of questions and I hope I can answer them. And I believe my contact details will be shared with the attendees at the end. And I do answer all emails personally. So please get in touch if you want to learn more. Aside from spreading this sort of information and helping people learn about this kind of thing, transparency is very important. And I know that Professor Gruss was talking about this, not just in terms of how the algorithm works, but how the business works. So in our case, we don't share or sell patient data. So transparency is very easy for us. In all of the countries where we operate, we meet data protection regulation laws. In the European Union, more or less, the GDPR is the strictest data regulation in the world, I would consider. I believe there's new legislation in Brazil, which is another country where we operate, which is also incredibly strict, and we operate there without any problems. So that's fantastic. And let me have a look. So we also advocate for the role of non-experts within the creation and design of AI solutions. And this is absolutely vital. It's one of the most important things. There's a great book called Zucked, which is about Facebook, and one of the earliest investors and advisors to Mark Zuckerberg, his name is Roger McNamee. And he says that one of the problems that they had at Facebook was there was a sort of widely accepted view that all of the problems could be solved by improving the coding. And yeah, this is not really the case. Not really. If we were robots, then our problems could be solved purely using code, but we are humans, and so what is required is a human touch. I have to say, personally, I can see the advantage of us all being robots. That would make things a lot easier for the people that deal with IT all of the time. But that's not the case, of course. So the human touch is very important. Okay, so that's everything I have to say. I hope it's been interesting, and I hope I haven't been talking for too long. I think I've done okay. I hope that people will continue to consider the non-technical aspects of artificial intelligence and consider that AI is as important as the human aspect, and especially when we're making technology that can affect huge numbers of people. So thank you for listening.
Thank you so much, Josh. That was an excellent presentation. I think we all learned a lot from it.
Thank you, Shaista.
You're very welcome. So I have a couple questions for you.
Mm-hmm.
This one is, can we use the system in the US? Are there, I know right now you're in Spain, but is there anything holding you back from bringing this technology into the States?
So I have to say this is not my area of expertise, but we've spoken to consultants in the US, and we believe it's not a problem. It wouldn't be considered a medical device because it's software and it doesn't diagnose. So I believe that wouldn't be a problem. And we are working towards a distribution contract in the US right now. So.
Okay, excellent. All right, and then I have one more question for you. So you mentioned that you guys based it off of about 600 photos to get your AI algorithm. Was the training set produced in Spain? And are there narrow representations in other ethnic groups? How do you feel about that?
That's a good question. I don't believe it was produced in Spain. I'm not actually sure where the data set was from, but what I can say is that we made very sure to include a large mix of different ethnicities and people from different races and different backgrounds. This was something included in the initial data set, which, as you said, was 684, I think. And it was increased a little bit later on when we added the ethnicity verification. So this is to check if you're doing phenomatching and you're looking for a facial resemblance between the patient and the donor, then one of the things we check is the ethnicity, of course. Mm-hmm. And so when we added that feature, more or less must be pre-COVID, probably about 12 months ago, then we spent a lot of time working with data sets with a large mix of ethnicities.
Okay, and you guys are still looking to expand on that data set, I think? Is that?
We're constantly looking to expand the data set, that's right. Yeah.
Right, so yes. Okay, well, thank you, Josh. That was a fantastic presentation.
Thank you very much, Shaista, and thank you everybody for listening.
Absolutely, and stick around for the Q&A between all of us. I will now like to introduce you guys to our next speaker, Professor Nicolas Bourdel, who is a professor of gynecological surgery at the Central Hospital University of Clermont-Ferrand in France. He received his PhD in computer-assisted surgery. He spent 1 year as an invited scientist at Johns Hopkins University. As a surgeon, he specialized in advanced laparoscopic procedures. Professor Bourdel has published numerous articles and made numerous presentations and conferences on minimally invasive surgery, perinatal environment, quality of life, and computer-assisted surgery. He is the founder and CEO of Surge AR, a company dedicated to the development of a software suite for augmented reality for minimally invasive surgery. The technology is mainly based on computer vision, artificial intelligence, and deep learning. Today, Professor Bourdel will speak about augmented reality in gynecological surgery. So over to you, Professor Bourdel.
Sorry, yeah. Thank you for this very kind introduction, and thank you for the opportunity to share our work on augmented reality. So I have to disclose that I'm the CEO of Sugar, the company that developed the software for augmented reality for minimally invasive surgery. So how we start to handle the problem. As a surgeon, when you perform surgery for infertility, you have sometimes myomas to remove, and you just look at the MRI of the CT scan or the ultrasound, and you don't have the exact localization of the myoma. And of course, you don't know exactly the localization of the uterine cavity, and you don't know really how to and where to start the incision for myomectomy. This is even harder for endometriosis surgery, for deep endometriosis. You don't know where are the ureters and where are the nerves. So we have to solve this problem as a surgeon. So augmented reality is probably one of the answers. This is just a very small example of augmented reality. So you have virtual information that you will add to the real world. So this is just a game, and you have this virtual information, which is Dark Vador, and you had it on the true place that can use the desk of your office to play. What are the ingredients for augmented reality? You have a camera image, which can be for the example, this truck, and you have a virtual object. So you have to do a fusion in between the virtual object and the camera image, but it's not just adding the image. You have to put the image at the right place with the right shape. So you have place plus deformation. This is exactly the same thing for laparoscopic or minimally invasive surgery. You have the laparoscopic image on the left side of the screen, and you have a 3D model of the uterus, the uterine cavity inside, and the myoma. And you have to fuse this image. So you will get the augmented image, which means you will have the information at the right place in the right moment. How it works. So we have to build a preoperative 3D models of the patient, of the organs, and of the tumor. So it's just with MRI, CT scan, or it could be with ultrasound. And we'll build a 3D model of the uterus and the myoma inside in the uterine cavity, whatever is the organ. We will see example later. How we can choose the right place and put the right information at the right place. In fact, this is the registration phase in the augmented reality process. That's the hardest part of the augmented reality process. So we really have to find correspondence in between the preoperative 3D model and the perioperative model. In fact, we have to build with the 2D images a 3D model, and then we have biomechanical algorithm to deform the preoperative model and to fit into the perioperative model. And then you can get the right information at the right place. Because if you had the 3D model in any place, it's exactly like this example. I mean, the car, the flowers are not put in the right place, so you don't get any right information. So we have to register this model, and then we can overlay the image, getting the fusion. So getting the augmented reality image. And then you have to repeat it very quickly because of course you will have movement of the uterus during all of the surgery. So you have to track the organs all over surgery. How do we solve this problem of registration and tracking? So why do you recognize this face? You recognize this face because you have the shape, you have the contour, you have the color of the hair, you have the eyes, and all of this is really computer-based vision. So we use exactly the same thing that the surgeon used during his surgery. What he used to recognize an organ. There's anatomical landmarks. This is a round ligament. There's classical contour that we know this is a uterus. You have the natural texture of the uterus, so you know this is the uterus. And you have biomechanical deformation that you can see it's a uterus and it's a hard or soft uterus. And you have the reconstruction that used as a surgeon, you will reconstruct the 2D images. We use exactly the same process with computer vision algorithm to track the organ all over the surgery and to do the researching process at the very beginning of the surgery. And we had also some deep learning algorithm. So this is just a Facebook example. So it will show you where are the walkers, where are the bicycle, where are the car. We use exactly the same process, but for organs inside the abdominal cavity. So we have to ask surgeon to segment the laparoscopic image, and then we get data, and then we try and train the algorithm to recognize the organ, and then it can do the registration process all over the surgery. So we use what we call intersection of a union to measure the effectiveness of our algorithms. It's just a concrete example that just with 400 images. So you see that the algorithm is not able to handle all the surface of the uterus or all the surface of the ovary or the instrument. The instrument, it's quite easier. And then it's after 4,000 segmented image. So we ask again surgeon to segment the shape and the contour of the uterus. So you see that the performance of the algorithm, it's quite perfect. And then if you have this information for the computer, you can restrict and you can track the organ all over surgery. And it's exactly how it works actually. So to summarize the principle of the augmented reality, you have the 3D preoperative model that can build with image. You have the 2D perioperative image, and then you will get the fusion. And here you can see on the video on the left bottom, this is what I have actually on my screen during surgery. So you can see really inside the organ. It's like the organ is semi-transparent and you get access to the tumor, you know exactly where the uterine cavity. Now more than 50 patients have been operating using this device. The first patient has been operating more than 4 years ago with this technology. And this is this patient, she get pregnant after a classical myomectomy using augmented reality. It's even more changing the paradigm of surgery. This is example of adenomyosis. So you know that adenomyomas, you can get very small tumor which are really hard to operate using laparoscopic surgery because you don't have the haptic feedback. And then here you can get the right position of even a very small tumor during the surgery. So of course we have to have more performance on our algorithm, but you can get access to very small tumor without having to use laparotomy. So you get directly access to the tumor. And what we can add also is really very new elements to help the surgeon to operate. Actually, when you do a laparotomy, of course, you use very standardized incision because of the shape of the fiber, of the muscle fiber. You don't use this kind of red incision. And in uterus, actually, you don't have any idea when you operate of the shape and the orientation of the fiber, of the muscle fiber of the uterus. But you can have this information using DTI during MRI. And then you can add it on during surgery. So that's what we developed also. Some augmented reality to help the surgeon to show the uterine fiber. Of course, the objective is to get a better impact in terms of healing and getting the best incision to get less traumatic surgery on uterus and of course increase the obstetrical project. So really it's a new information we didn't even think we can have access to. And this is because of augmented reality. So you can calculate mathematically, preoperatively, the best incision, including the data of the fiber, the exact localization, and then you can get access to the uterine cavity or aspect it. So you have all the information and you can decide before surgery which is the best incision, what is the best incision, and show it to the surgeon at the beginning of surgery. It works also for partial hepatectomy, so it's even more relevant because we can show the surgeon exactly the exact best incision to expect a free margin around the cancer. And you can calculate what is the best incision, whatever is the orientation of the instrument. It works also for partial nephrectomy during robotic surgery. You can see example using the Da Vinci robot for partial nephrectomy. So you can see also that there is a vascularization. We are able to show the vascularization, or whatever is the information you get access before surgery, you can show it during surgery because you have the restoration. So you can really show everything you have on the CT scan or the MRI before surgery. So this is really, we are teaching the computer how to read the operative field. There's deep learning. And of course, if you can imagine adding that to a robot, you can imagine at some point replace the entire surgeon. This is not a dream, and this is maybe not the next future, but this is a decision-making tool also. The open question is still, probably there's something to imagine for the embryo transferred. And what are my other question, which insurance has the ART specialist will you choose for your infertile patient with adenomyosis or endometriosis? Would you use the classic one or the augmented one? So thank you again for your attention.
Well, thank you very much, Professor Bourdel. That's just so fascinating, augmented reality and all these tools that you are developing. We have some questions here, so one or two questions before we move over to Veronika Magdanz for the last lecture of this session. So what fields of medicine is AR being used already? This did start quite a while ago, I think, so several years at least. What fields of medicine is AR being used and maybe being used successfully? And once doctors get into this, I presume they become dependent on it, which is probably a good thing. And once they're trained in the usage, do they stick with it, or do you see people abandon it and say, well, it's not good enough, or I don't think it's helping me? But what's the reaction in the field?
So you have really strong data for neurosurgery, but it's called neuronavigation. But it's a completely different principle because it's neuronavigation for a neurosurgeon works like GPS. So you have some like ball in the instrument, and you have like satellite in the operative room. So you can get access to the exact position of the instrument of the surgeon and the patient. And of course, you can really screw the head of the patient, and then you can also have CT scan during surgery. What we handle, it's completely different because the shape of the organs, the place of the organs will be completely different in between the preoperative images and the perioperative images. So you really have to include strong algorithms that are able to predict the biomechanical deformation, which is really very dependent of the organs. So it's an entire new field for laparoscopic surgery, at least. So we use it for gynecology. It's the very beginning of the process, but the objective is to use it in any kind of laparoscopic surgery, because if you have the camera at the human surgeon, you can't handle all the information you have on the screen. And the best example is when you are two surgeons. I mean, one of the surgeon is more focused on bleeding, for example, the other one on getting access of the tumor. Of course, if you imagine having this artificial intelligence or computer vision had during surgery, it's like having at the end, like 10 experienced surgeon that will help you. That's really, this is very basic explanation, I know, but this is the end objective for developing this kind of aid. So actually, as surgeon, you have to have a very simple software. It's really UE and UX experience that is very important in this kind of software during surgery, because you don't want to lose any time. So really, it's a completely different port. But it is really during surgery, the software must be very easy to handle. That's another problem we are facing for this kind of development of this kind of software. Yeah.
Okay, great. Well, thank you so much. It was a wonderful presentation.
Thank you.
Stick around, because we'll be back in about 15-20 minutes for more questions for you. And thanks again.
Thank you.
So it's my pleasure to introduce our last speaker, last but not least, Dr. Veronika Magdanz from Barcelona. She's a German biotechnologist who has been developing sperm-driven and sperm-templated micro-robots for over 7 years. It's a super fascinating field, particularly for us here and our audience. She studied biotechnology at Braunschweig and chemical engineering at the University of Waterloo before pursuing her PhD at Dresden University, and Oliver Schmidt's team at the Institute for Integrative Nanosciences. And she is currently working as a Theodore Linden Fellow at IBEC Barcelona in the Smart Nanobio Devices Group. Lots of toys, I'm sure. Her interests span from sperm motility and metabolism in complex environments to the development of smart micro-robots. She is interdisciplinary. She jumps, as do most of the speakers today, she jumps from nanotechnology, robotics, material science, chemistry, and biology. And she is a loyal follower of I3, so we're proud to have her here. She has co-authored over 30 peer-reviewed articles in high-impact journals. So, Veronika, welcome, and we're looking forward to your presentation.
Thank you, Jacques. Thank you very much for having me. And first of all, thanks for organizing this. I've been really enjoying the last few sessions, and there's more good ones to come. So, yeah, thanks for organizing this. So today I'm going to take you into the field of microrobotics a little bit, because I'm sure it's unfamiliar to many of you. And I'm going to talk about sperm-driven and sperm-templated microrobots, just as one type of biohybrid microrobots. But let's take a step back and talk about micro-nanorobotics. Where does this actually come from, and what's the motivation behind it? And it's a fairly young field of research, but already 60 years ago, in 1959, Richard Feynman gave a very famous lecture called "There's Plenty of Room at the Bottom." If you're interested in some history of science, you should look it up. And in that lecture, he drew this vision of miniaturization of medical operations. And he says, imagine you could swallow the surgeon, and it could go around inside your body, find a diseased site and cut it out or treat it. And the surgeon wouldn't have to cut you open, but it would be non-invasive. So now, 60 years later, we have the technology to start making this vision come true. But there are lots of challenges. One of the main challenges is autonomous motion on the microscale. So we cannot simply downscale our macroscopic motion mechanisms, because the physical phenomena on the microscale are so different. So we have to come up with other solutions. Also, we need very precise control mechanisms in terms of, so it needs to be remotely controlled and non-invasive. And of course, in the end, we want these robots to be able to perform certain tasks, such as catching cells or killing cells, or delivering a drug or a cell to a target location inside the body. And a field within microrobotics is biohybrid microrobots. And this simply means we combine biological and artificial components. Why biological cells? Biological cells have evolved to operate very efficiently on a microscale for a very long time. And they are very fast moving when we think about bacteria or sperm cells. And they have a huge variety of sensing and taxis abilities. So the ability to respond to their environment and adapt to it. And some even have the ability to repair themselves, which is very hard to do with purely artificial components. And then we combine these biological components with artificial compounds to bring in our desired functionality. This can be through the choice of material. For example, if we bring in some ferromagnetic material, we can make it responsive to magnetic field, or through the geometry or topography, or many more options. So, and within this field, I specifically am interested in using sperm cells. Why sperm cells? Well, they have a very powerful driving source when we look at their flagella. They carry information. So they have the DNA inside the head, which is crucial for fertilization. They can be a drug carrier. I will come back to this in a few minutes. They can be the cargo when we think about applications towards assisted fertilization. They are also very smart sensors. So sperm cells have been found to respond even to a single molecule and be able to redirect their motion accordingly. And they're very well adapted to move in physiological environments, which is very important for microrobots in biomedical applications. They need to be able to move in body fluids or in very viscous environments. And also their intrinsic flexibility is an interesting point, which I will get back to you in a few minutes. So the first approach that we did was we took bull sperm and we captured them in these microtubes that we fabricated using different nanotechnology fabrication techniques. I will not get into the details of the fabrication, but we basically take nanomembranes that are really just few nanometers thick, and we can tune the length and the diameter in a way that they can fit single sperm cells. In this case, these tubes have titanium and iron in them, so they are responsive to magnetic field. And then they are tailored to fit single sperm cells. So capture them, and that what it looks like in real time is that the sperm cells get trapped and start pushing these tubes forward. So the cells are very powerful, able to do that. Now we can bring these sperm-driven microtubes in a setup of electromagnetic coils. So this is basically a setup that provides a magnetic field that's not very strong. It's less than 2 millitesla, so it's not harmful to the cells. And in combination with a image recognition system, we can then tell this system to bring our sperm-driven tube from point A to point B, and a very simple proof of concept to show that we have this remote control over single sperm cells inside these microtubes. Now you might wonder, okay, what if I want to release the cell again? It's great to be able to guide them, but what if I want to deliver them, for example, to the egg cell? So what we did, we incorporated thermoresponsive polymers in these nanomembranes. That means that this material is able to respond to temperature change very sharply, in a sense that at a slightly decreased temperature at 30 degrees, we're able to capture sperm cells. And as we increase the temperature to 38, which is optimum for bull sperm, these microtubes open up and can release the cell. So again, this is a remote mechanism because We just need to change the temperature, but of course this is just the first step as a method to release the cells locally. Then further, we tested the motion of these sperm-driven tubes in more realistic environments. In this case, we isolated oviduct fluid from the cow, which is very viscous fluid. It's about 10 times higher in viscosity than the sperm medium we usually work with in the lab. But we saw that even there, the sperm-driven tubes are still able to migrate through and to move forward under these conditions, which makes it very promising for usage in body fluids. Then here's some work that is mostly done by my colleagues in Dresden, by the IFW, and they are using the sperm-driven robots for drug delivery. In the first example, they loaded the cells directly with relatively large amounts of anti-cancer drugs and found that the cells are still able to move forward. So the cancer drug doesn't impair the sperm motility too much. Then these drug-loaded sperm were loaded or captured in 3D printed microstructures. And these were led again by magnetic field to a tumor spheroid, which in this case is just a model for cancer. And then by mechanically releasing the sperm cell, it's able to bring the drug into this spheroid. And in a very recent study, they also showed that these sperm-driven microrobots can swim in the bloodstream, which was demonstrated by having a slightly diluted blood sample in a microfluidic chip. And the nice feature here that we see is that sperm cells, we know that sperm cells can swim against the fluid flow. It's called rheotaxis, and that this can be used in this context, for example, for heparin delivery in case of blood clots. Here's another type of sperm-driven tube, and these consist of gelatin. Why did I choose gelatin here? It's not only biocompatible and biodegradable, it's also pH responsive, and we can load it with drugs. And it is an antioxidant. That means it can protect sperm cells from oxidative stress. And what I did was I loaded these gelatin micro cartridges at pH 5 with heparin. Heparin here is used as a agent to induce capacitation in sperm cells. Then we capture sperm in these heparin-loaded structures at pH 5. And because gelatin is pH responsive, when we change the pH to pH 8, the heparin is locally released and triggers the sperm capacitation on board or in situ. Now, we know that sperm cells swim through a variety of pH during their journey to the egg. So this is all an environment that is also found in the reproductive tract, and could also be used to track the pH or to use the local pH for an in situ sperm capacitation. As I mentioned before, this gelatin also has been found to scavenge reactive oxygen species. If you want to know more about the data, you can go into the publications and look how we did it. Now in the last part, I briefly want to talk about sperm cells as templates. So in this case, the sperms are not motile anymore, even they're not alive anymore. But we're interested in using the flexibility of the tail that has basically evolved over millions of years to be efficient swimmers. And what we do is we combine these sperm cells with nanoparticles, and by a simple electrostatic interaction between the particles and the cells, we can get the sperm covered with nanoparticles. Here we call them iron sperm. And what we can do then is we use a 3D magnetic control system that creates this actuation of the cells. So these cells are not alive but they're moving due to the magnetic actuation. And we can analyze the frequency, and we can increase the frequency, make them move faster. This is, on the one hand, a very facile method to get flexible robots, which is interesting from a robotics point of view. And at the same time, we can use the system to study the biophysical parameters of sperm cells, such as the bending stiffness. And to demonstrate here some potential biomedical applications, we also loaded these sperm cells with a cancer drug, and just to show that, yeah, this is possible if you work with biohybrid robots, where you can easily use the organic body to load biomolecules. And another nice feature of the nanoparticles on the sperm cells is that we can image swarms of these sperm in ultrasound, because the particles really increase the echogenicity of these sperm cells. So with that, I'd like to summarize my talk and want to just say that we demonstrated this remote magnetic guidance of sperm and thermotriggered release of sperm. We showed that sperm cells are also promising for drug delivery, and that we can use smart microstructures for the biochemical manipulation of sperm cells to enhance fertilization capability, and that we can make flexible microrobots based on sperm cells as templates, and that these are also promising for in vivo imaging of sperm swarms. With that, I'd like to finish, and thanks for listening. And I'm very thankful to the team and my hosts and collaborators that are near and far and make this project exciting and successful. Thank you very much.
Thank you so much, Veronika. Wow, that was an amazing presentation, and I really enjoyed all of the video. One question we have for you, it's a little far off. I don't know if you want to answer this, but could you perhaps one day add a motor to the blastocyst and make it modal? And do you think it would be a possibility in the future to guide it to an implantation spot?
I think that is a very good question. Actually, I believe that a group in Dresden is working on this, if people are interested in that, it's probably a good idea to talk to Dr. Medina Sanchez in Dresden, who's also working on micromotors. So what I also need to say is there's a huge variety of micromotors, okay? And today I only had time to talk about the ones I've been working on, but there are also many different ones, for example, enzyme-driven or light-driven or bacteria-driven, many different ones for different applications.
Okay, fantastic. I'm going to ask you one more question before we move on to our open-ended Q&A. Using sperm robots, are you at all worried about autoimmune or an immune response?
Yes, this is also a very good and important question. We have not investigated this part, and I think as we move more into in vivo environments, we will have to investigate this very much. So there's some points. So we have this smart microstructure surrounding the sperm cells, which might also be able or enable us to deal with that in a way that, for example, we can load it with certain immune response suppressants, or yes, also maybe we can work within a certain time frame before the immune system comes in. But definitely this will have to be addressed in the future.
Okay, fantastic. Thank you so much. Okay, Jacques, shall we open up the Q&A for our audience? Do you want to ask the first question?
Yeah, thank you everyone for your lectures, and there's quite a few questions here. So, I mean, staying with you Veronika, a little bit of a question on the edge here is, can microtubes be used to keep sperm out of a certain area? I mean, could you use them in an anti-conception way?
Mm-hmm. Yeah, also a very good point. Something we've also been thinking about. maybe another a little story that goes into that direction is when we were when the sperm bots are used for drug delivery, for example, sometimes the question comes, okay, what if the drug is delivered but then also the woman is pregnant, because we also have the sperm? So it's a similar question. But for the contraception, definitely is an area that needs to be explored. What we could imagine, for example, is having agents on a smart microstructure that basically makes them immotile or keeps them from getting beyond a certain point in the reproductive tract.
Right. So these microtubes, are those difficult to make?
They are not difficult to make if you have the equipment. So
Okay.
it's possible with standard fabrication techniques in microtechnology or microfabrication.
And so what's the dilution factor here? Do you have to add 1,000 to capture 10 sperm, or do you have to, or is it much better than that, more efficient than that?
Yeah, it's more efficient than that. It also really has improved. When I started my PhD, I think it was around 1 or 2% capture rate, and I think now it's a lot higher. I can't tell you exactly,
Okay.
but I would say it's around 30–40%.
Oh, that's great. Yeah. Okay. Some questions from the audience for Josh. A question from Rahul Sen, who is asking, how is age taken care of or considered while performing phenomatch? Is age-specific donor selection done, or are younger donors selected for younger recipients?
Thank you. That's a great question. Age is very simple. This is just simply a number that the user can input. So in that sense, phenomatch doesn't really have to get involved in terms of facial matching. So to answer the question, no, we don't match donors and patients in terms of their age, just in terms of the facial similarity. In the case where age is important, it's very easy, of course, for the doctor to look at the ages of the donors and patients. So that's how that's done.
Yeah, and age, of course, egg donor age is, of course, relatively narrow, right? I mean, so you're not looking for 18-year-olds, and nor are you looking for 42 or 45-year-olds. So it's a relatively narrow age group. Don't you think so?
That's right. But what you have to remember, of course, is that the age of the patient that we're doing the match with does vary, of course. But luckily, the algorithm is fairly stable in terms of age. I mean, you saw the photograph of my mum and my brother. The phenotype is still very much visible. That's something that eventually it does go away and it becomes less obvious, but only towards, the very much the end of your life.
Thank you. Shaista.
Okay. So the next question I have is for Eyal. However, I think anyone can answer this question if they want to. In your opinion, what is the most amazing function that computers and AI specifically can now perform?
So this is really a wide topic. From the computational point of view, in recent years, it was possible to solve Go, which is a very difficult mathematical problem. I'm referring to the game, the Eastern equivalent of chess, which is much more difficult from a mathematical point of view. And people working on this thought it will take maybe 1 more decade to solve. And already a few years ago, they were able to defeat the top world champions. So this is from a computational point of view. Maybe from a moral or social point of view, I think the ability today to better and more easily allow different cultures to communicate via translation, either for a text or for a speech, is a very important function and will get more important as these methods apply to more languages and more accents. And finally, I know just about a specific application in medicine. But recently, there was a work by Google where they were working on finding some disease in the eye, in the retina. And by mistake, they found out that actually the retina contains information allowing to predict with very high confidence if the person is male or female. And this is a signal that was not known before to exist in the eye. And maybe we will find many more interesting things like this. So applying, for example, deep learning to time-lapse videos of embryos, maybe it will be possible to replace various invasive tests, and maybe there's more data in there than we are aware of today.
Okay.
If I could just add something there.
Mm-hmm.
There is a fantastic documentary which is on Netflix called AlphaGo, which is about the algorithm that was created that beat the #1 player of Go, the #1 human player, and it is one of the greatest. If you love Black Mirror and AI ethics, it's absolutely fantastic. Firstly, because it's real, of course, it's a documentary, and secondly, because for me, the most incredible thing about that documentary is that when the creators realize that their algorithm is going to win, they're not happy about it at all, because everyone is rooting for the human in that situation. So, I mean, of course, you know what's going to happen at the end. The algorithm wins. But the AlphaGo documentary, it really is fantastic. I'd recommend it.
That's amazing. I'm going to add that to my watch list. It's a little scary to think that humans are the underdogs in this situation that everyone and actually, I'm going to ask one more question to you specifically, Josh. So in terms of confidentiality of donors, I know in some countries, we have very strict anonymity rules, and I know it differs from country to country, but how do you think Phenomatch would handle that?
Thank you. This is a great question that I love answering. So we have anonymous donation in Spain, which is where we're from, and also where the majority of our clinics are. So we know that in terms of confidentiality and anonymity, Phenomatch is an incredibly powerful tool, because the privacy and the anonymity is protected, and we are still able to get those results from the donor databases. So yeah, in terms of legislation, I think in almost, we work in 4 continents now, I believe. Is Russia is Europe and Asia, that's 2 continents, right? Okay, so it's either 4 or 5 continents, depending on how you think of it. But we work in many different countries with many different legislations, and we have no problem. Essentially, the short explanation of this is that the face is considered medical data. And so the clinic or the bank also already has medical data on the donor in terms of, blood type, DNA test results, et cetera, et cetera. So the face is, considered part of that. Thank you.
You're welcome. Jacques, do you want to ask a couple more questions before we wrap up?
Thank you. Question for Prof. Bourdel. Actually, several questions here. Embryologists are a bit like surgeons. They use micro tools, which are like surgical tools. They cut, they stick, they make incisions, or at least used to. Could augmented reality play a role on that resolution? I presume it does, because the resolution is not an issue when you use microscopy and visualization. So can that apply to our field? For example, could you use augmented reality of the ovary for better visualization of follicles? Could you look at maturity? One thing when an IVF doctor sticks follicles, they go for size mostly, and they go for proximity and how easy it is. How many can they get at the same time? Which makes sense, and how can you avoid, of course, blood vessels and all that. But can augmented reality help you with things like cumulus maturity. So where there is a lot of fluid between the cumulus cells that are surrounding the egg. Now the egg, at the time of egg retrieval, the egg is at a resolution that you can hardly see. But the cumulus stalk and the follicular cells surrounding it is one, you know, up half a centimeter, 7, 8 millimeters, 10 millimeters sometimes. So that's a lot of stuff. Could you look at that and use augmented reality to help you out selecting? I guess this person is just guessing, but it's a good question, maybe.
Yeah, this is a good question, and the answer is in the question. I mean, you spend so much time like explaining you have like haptic problem, you have like really finally human problem in taking the decision. So of course you will have you can get some help from the computer. Technically is more the field of Eyal, I think, because in augmented reality, as we use it in surgery, you have to have another information, a preoperative information, which means the image. But I mean, the next step will be development of, as I told you, like smoke detection or bleeding detection. So, and when you have this information and you use a deep learning algorithm, you can really help. Anytime you have a task, you can help the human, and you can. We know in surgery that many complications come from the interruption of task. So I think you really have the same problem when you have a human procedure. So if you can help the human to go through all the procedure, guiding him, of course, this is augmented reality, and you can really help him getting the right target and really also remove all the movement of the arm and all this part of the human task, of the human procedure can benefit from the help of a computer. Whatever if the algorithm under it could be deep learning again, or based mainly on computer vision. So really, sure, it can help.
Yeah. So there's an area of general questions, and one of the questions from the audience here is, how many years will it take for people are impatient always when they see something fantastic and new. They want it now, and of course we want this now. So in how many years this person is asking, will AR be a companion to almost all medical operations, all medical surgeries? What do you
just
think?
From my personal view, I started my PhD. I mean, I started working on it 11 years ago. So really, it's a huge and a very long way, and it's a very it's a branch of artificial intelligence, but it's really based mostly on mathematicals and really mathematical problem. But going to the R, I mean, in our example for our company, the objective is to get the CE mark next year. So I hope it will be available on the market next year. But again, this is a medical device, so you never know what's going to happen. You have to have very strong data to get the CE mark. And so the CE mark, it's quite the same now than the FDA approval, but this is a very long way. So it's quite a different procedure than Phenomatch, for example.
Yeah, of course. And with CE marking and FDA approval, you hope that there is a match on the other side and that there's somebody thinking on your level. And that's not always the case. And I realize that. So there's a lot of hold up on AI proposals in general, the FDA level, is what I've heard. But yeah, thank you for that. A question for Veronika. Let me see. Yeah, this is it's another question out there. What's the possible use for micro-robotics and microgravity? And the reason this is being asked is next week we have a session on the effects of space on reproduction. And of course, I don't know how spermatozoa swim. Do you have any idea? Do you have any idea? Am I asking a question that's probably difficult to answer?
I mean, it's a good question. If we don't know the answer, right, we can start discussing. I believe that gravity wouldn't play such a big role from a scientific point of view, but we don't know. And I think it would be a very good experiment.
Yeah.
To start even just looking at sperm motion in microgravity. Yeah, I have no idea.
I just want to note that I read something about this very recently, and I'm talking about the last couple of months. I think it was sometime in July, and the way that it's about the way that sperm move, and it's something like a spiral.
Yes, that's right.
But I can't give you any more information than that. But
I think that has not been known for quite a while, but it was well it was well reported in a PR perspective, I think. But
yes,
yeah, we know that's how they move. It's a corkscrew movement almost.
Yeah.
And I think if you look at video nowadays with good resolution, you can almost see that. But the image analysis of spermatozoa, which is pretty advanced, can show that. But yeah, thank you. Well, we are at 4:38, Shaista. What do you think? I think we should probably wrap this up. We have a few minutes, and we have a surprise because we're going to give away a subscription to Reproductive Biomedicine Online, but you have to do something for it. So thank you again, everybody. Thank you, everyone, for taking time to participate in this session and this discussion. And I particularly like to thank our speakers, Eyal Gruss, Rackstraw, Professor Nicolas Bourdel, and Veronika Magdanz, and of course, my co-moderator, Shaista Sadruddin. So please, Shaista. Yeah.
I would like to thank each of our speakers as well for participating on our platform and giving our audience some great insight into the world of AI and augmented reality. I truly think we can capture the potential that this has towards the future of IVF. I would also like to thank the organizing committee of this initiative, Dr. Peter Nash, Thomas Elliott, Giles Palmer, Dr. Jacques Cohen, and Marianne Savetics. Thank you all for the huge amount of work we spend on this endeavor. I also want to give a shout out to today's triage team, Dr. Liesl Nathamat, Marianne Savetics, Anna McLaughlin, Giles Palmer, and Dr. Peter Nash. And as Jacques already said, today's session was produced and organized by Dr. Energy himself, Giles Palmer from Wales. So a big thank you to you, Giles, for organizing everything. Now, as promised earlier, yes, big applause. As promised earlier, it's time to do a quick quiz and ask you 3 questions. If you know the answers, please write them into the chat. The first person who answers all 3 questions correctly will win a 12-month subscription to RBMO. Okay, Marianne, go ahead and ask the questions. Number 1, whose law refers to the speed and capability of computers to increase more or less exponentially every few years? Question 2, what does the T in CAPTCHA stand for? And number 3, what is our next session called? No clue. Okay, so Liesl knows the 3rd one. And please post all 3 answers on the same chat line, everybody. Giles says no cheating.
That's not a very human thing, not cheating. So.
Yeah, I got very overexcited because I knew the first one and I wasn't expecting to.
And there's a hint written for question number 2. So the T in CAPTCHA stands for a computer scientist.
Yeah.
Biologist.
He wasn't treated very well by his government. That's another hint.
Big hint.
And he became more famous with time after his death. So he's Very famous now.
You know, another clue for number 2 is that there's a statue of him in Manchester eating an apple, but it isn't Steve Jobs.
Now it's we have somebody who has guessed the second question.
We have an answer. It looks like the first correct answer was posted by, oh, let me scroll up.
Audrey.
Congratulations.
I think that's good enough. Oslo, Turing, and reproduction and space. It's reproductive biomedicine in space, but that's good enough, right? We declare you the winner.
You are the winner. Congratulations. We will be in touch with you shortly for your 12-month subscription. Marianne, you want to post the answers for all of us just so the audience can see? There we go. Moore's law. No, the answer to question 2 was Turing. And our next session is reproductive biomedicine in space. Okay. All right, Jacques, over to you to close shop.
Thank you, Shaista. Thank you so much for being a co-moderator today and had a good time. Also, my thanks goes out to Charles Palmer as well, who put this session together. Remember, all these sessions are recorded. You can always go back to them on our website, ivfmeeting.com. Well, if you thought this session was a bit crazy and weird and different, that's good. Check out our next one a week from now. That session is entitled Reproductive Biomedicine in Space. There will be another Palmer production. Giles will co-moderate that one together with Liesel Nel-Tomaat. The speakers will be discussing general physiology in space, birth control in space, birthing in space. Can you imagine that one? Sperm function in space, effects of radiation and microgravity on general physiology and reproduction. It will be held at the same time in space as today, next Tuesday on I3, October 13th at 3 p.m. Eastern Standard Time. So if you're in Western Europe, that's 9 o'clock in the evening. And in the UK, that's 8 o'clock. And if you're very daring, you go further east, like Israel and the Middle East, it will be about 9 o'clock. No, 10 o'clock. And then you go further out to India, you're looking at midnight and beyond. I'm always surprised how many are attending from India. That's very good. We'll be hearing from Dr. Virginia Wotering, Dr. Farsha Jain, Dr. Fathi Karuya, and Dr. Sheila Sadruddin. Another Sadruddin and the same initials as Shaista. There will be 2 Sadruddins in space, okay? So see you all soon, and please be safe. Take care.
Thank you, everybody. Bye.